Hello, everyone, and welcome to Worksheet 3 Video Key. And we are starting Chapter 3. So I will switch to my document camera so we can get started. So we're starting to talk about curved arrows that are going to be used to show how electrons move or transfer in organic reactions, right? So this is a little bit different than the concept of resonance, which was in the last part of chapter 2, which showed the movement of electrons in unhybridized p orbitals. And so we are going to just remind ourselves about curved arrows, right? They start from an area of electron density, which could be a bond or it could be a lone pair. And then the arrow head points to where those electrons end up. So they're either going to depict the formation of a bond, and we do that by pointing directly at an atom. They could also depict the formation of a pi bond, in which case we would typically move it to between atoms to show a secondary bond forming between those two atoms. And they could also end up as a lone pair, and for that we would also point directly at the atom. So let's go ahead and look at an example in question number 1. It says an acid-base reaction uses the following curved arrows to depict electron flow. Label the components as acid-base, conjugate acid, or conjugate base. So hopefully you learned from the lecture video that a base is something that takes a proton from an acid. And this is the Bronsted-Lowry definition of an acid and base. Okay, so we're going to label this the base because it is taking this proton from this acid, and the acid loses the proton but keeps the electrons in the bond to that proton, which is the nucleus of a hydrogen atom. So the arrows, right, we've started on a source of electron density, which is a lone pair. We point directly at the hydrogen atom to show that we're going to use these two electrons to form a bond between whatever B is and the proton. And then we use this arrow to show that these right now sigma bonded electrons are being moved to form a lone pair on whatever A is, which is going to be the acid once it's lost its proton. We'll label this as the acid. And then in reverse, right, if we were doing the reverse reaction, this would be the species that takes the proton, right? So this would be the base, but because it's on the right-hand side of the equilibrium arrow, we're going to call this the conjugate base. And then the species in reverse would lose its proton, right? So this would be the conjugate acid. And then the question number 2 asks us to draw the curved arrows for the reverse reaction. So we should start on the base's lone pair, right, or its source of electrons. Point directly at the hydrogen atom to signify that it is going to form a sigma bond to that hydrogen atom. Then we take the electrons from the bond and point directly at whatever B is, right, which will be what leaves with its lone pair. So this would be the appropriate way to show those curved arrows. Notice that they're always starting on a source of electrons and they're signifying either the formation of a bond or a lone pair. All right, let's move on to question number 2 that says, use curved arrows to show the chemical reaction between we just did question number 2. Question number 3. Use curved arrows to depict the following acid-base reactions. In the empty box, predict if the equilibrium of the reaction will lie to the left or to the right, as shown, based on your knowledge of weak and strong acids. Recall that these acids are strong acids, but you can then apply that if it's not one of these, it's a weak acid. And the first example has been done as a reference. So if we look here, we see that they're showing water as the base, taking this proton, and it ends up forming hydronium ion. The electrons are left behind to form chloride from hydrochloric acid. So they've shown us the curved arrows, and then because hydrochloric acid is a strong acid, we've predicted the equilibrium will lie to the right? Because strong acids completely dissociate in water. Okay, so let's go ahead and work on the next question. The arrows should look really similar between HCl in water and HF in water. You can really just kind of copy those arrows. Notice I'm drawing them this one a slightly different way. That's okay. And we want to predict the position of equilibrium. Well, HF is not a strong acid. It's actually a weak acid. With pKa of 4, whereas HCl's pKa is something like -7. So this is a much stronger acid than HF. Because HF is considered a weak acid, the position of equilibrium will be to the left, right? So the equilibrium should point towards the weaker acid and base, but in this case, we're just looking at the acid. Okay, so moving on, right? The next one shows us sulfuric acid and water. Right? So water is still acting as the base. Sulfuric acid is a strong acid. So it will take a proton from sulfuric acid and we'll leave those electrons behind as a lone pair, which we see on here. And then again, sulfuric acid is a strong acid, so it's going to dissociate. So we're going to point towards the right. And then nitrous acid is another weak acid. So it is predicted, right, that we're going to not have much dissociation in water. And notice that it's HNO2 and not HNO3, right? Those are different. Nitric acid is a strong acid, but nitrous acid is not a strong acid. And even though it's not a strong acid, it's still going to act as an acid. So we can draw an acid-base reaction. We'll take water over here and pick up that proton and then leave behind that lone pair. Okay, let's look at the factors that govern relative acid strength. So if you've watched the video, the lecture video, you know that they talked about an acronym called ARIO, A-R-I-O. And A in ARIO stands for the atom. And so that's what we're going to be talking about first. We're going to be talking about an atom's ability to stabilize a extra lone pair and the resulting negative charge, so extra electron and the resulting negative charge that results from that. And that will help us with one thing that we need to understand about predicting the position of equilibrium in an acid-base reaction. Okay, so this talks about the fact that increasing base strength on the periodic table goes up and to the left, which means that the opposite is also true, right? So if you take an atom and you're going to the right or down a periodic table, then the base is going to be, if the only difference is the atom, the base will be more stable in that direction. So sort of think of stability and reactivity as inversely related. So if something is more stable, it's not going to be as reactive a base, and we'll call that a weaker base. If something is less stable, it will be a more reactive, stronger base. Okay, so let's look at this. I actually think this is not, yeah, that's a little better. So base statement above, number 4 says, rank the following in order of increasing base strength, with 1 being the strongest base. So that sounds like it wants us to figure out what's going to be the strongest base, label that 1, and then move down to 5. Right? Well, if you think about where these atoms are on the periodic table, we have carbon, nitrogen, oxygen, fluorine, and then down 2 would be bromine. So if base strength, right, increases as you go up and to the left on the periodic table, then carbon with a negative charge should be the strongest base. So these are actually nicely already sort of ordered for us, which is convenient. So again, activity and size. So as you go from 1 to 4, you're in the same row of the periodic table, and electronegativity increases. That also increases an atom's ability to stabilize a negative charge. Remember, more stable means less reactive. So it makes sense then that fluorine in this row of 4, right, would be the least reactive, because it's the most stable base. And then the difference between 4 and 5 is size, actually, not, there's a difference in electronegativity, of course, but size is the dominant factor. And specifically, an atom with an extra electron and a negative charge is more stable on a larger atom because of the greater area that electron density has to spread out. Kind of different, but in a way, the same idea of resonance, right? If we delocalize electron density over a larger space, then those electrons are more stable. It's the same idea, even though we're not dealing with spreading the electrons out over multiple atoms. It's only on one atom, but a larger atom, which has more space. Okay, so next it says to draw the conjugate acid of the bases in the previous problem number 4. So if we draw the conjugate acids, all we really need to do is, instead of having a lone pair and a negative charge, attach a hydrogen atom there. And just for clarity, you can go ahead and draw it in. I know with line structures, typically we don't draw the C, right, and the H attached to it, but it's okay in this case to kind of really highlight it. And then in this case, we would have an H2, would have an alcohol, next case, right? And we'd actually have a lone pair and 2 lone pairs. We don't need to draw those in, but you can. And then we have HF, right, and HBr. These are all the conjugate acids that we're looking at. And remember that strong acids produce weak conjugate bases and vice versa. So if you actually looked at the previous page, you might remember that HBr is a strong acid. That actually makes sense because we predicted bromide to be the weakest base, right? So it wants 1 with the strongest acid. So it's just going to be inversely related, right? Where we're just going to go in the opposite direction than we did with base strength. So it makes sense. This is the strongest acid, so this is the weakest base. This is the weakest acid, so that's the strongest base. And then if you actually knew pKa values, you could use that to justify your prediction here based on the atom. Specifically, the pKa of an alkane is typically somewhere between 44 and 50. That's very weak in terms of an acid. The means are typically anywhere between 35 and 38. Alcohols are typically anywhere between 15 and 17. HF is 4 and HBr is -9. You can see that there's a definite trend in lowering pKa as we go from left to right. So knowledge of pKa values can be really helpful because it's a surefire way to know the difference between, acid strength. Okay, so next question says, based on the relative base strength in the previous problem number 4, predict the position of equilibrium in the following reactions as written, right? And then it talks about big picture. Equilibrium lies towards the more stable, weaker base, right? So you predicted the base strength in question number 4. So all we have to do is draw the equilibrium towards the weaker base, right? So the first thing we would want to do, of course, is identify what is the base and what is the conjugate base so that we can compare those directly. Right? And in this case, we have a carbon with a negative charge versus an oxygen with a negative charge. We said that the carbon with the negative charge was the strongest base, right? So this was the strongest, and this was weaker, right? So maybe stronger, weaker, right? And then we're going to predict that the position goes towards the weaker base. Okay, looking at this again, we need to draw in what is the base, right? And what is the conjugate base? And then we can think about which one should be stronger and which one should be weaker. So remember that fluoride was actually a stronger base than bromide. So we're going to write in stronger, weaker, and predict the opposite in terms of equilibrium. Next, we have this nitrogen base and versus carbon as the conjugate base. Right, so again, carbon with a negative charge will be stronger than nitrogen. Right, so remember that we're going for the weaker. We should predict our equilibrium that way. And then in this case, now we have a sulfur base and one that deals with an oxygen atom. So what's the difference here, right? So these are actually, oxygen is above sulfur on the periodic table. So the most important difference here is actually not electronegativity, but size, right? And we said that larger atoms have a better ability to stabilize a negative charge due to the increased sort of space. Think of it as like entropy, right? The increased amount of space that the electron has, right, to spread out over increased, is the word I'm looking for with entropy, disorder, essentially. And so this one is going to be the, so if it's more stable, right, it's the weaker base, and this should be the stronger base. So again, we're going to predict going to the left. All right, that was the end of that activity. Hopefully you found it a quick one. Let me know if you have any questions.